I believe that nuclear fusion is the energy source of the future, and it'll come eventually, maybe even before the sun will blow up to a red giant and swallow Earth. The question is just how. In the past years, we've seen one particular technology make rapid progress: stellarators. And in the last few weeks alone, major announcements from 3 different companies have demonstrated just how quickly the technology is coming together. Fusion has long promised the holy grail of energy, a near limitless, clean and safe power source. The trouble is that if you have nuclear plasma hot enough to fuse, it's incredibly difficult to control. The most used and most researched approach to do that are tokamaks like ITER. They use a combination of magnetic and electric fields to keep the plasma floating inside a torus. Tokamaks continue to break records. In January, the Chinese East tokamak controlled plasma for over 1,000 seconds, setting a new world record. But just a month later, the West tokamak in France set a new record by maintaining plasma for over 1,300 seconds. These are impressive records, but there's no nuclear fusion happening in these plasmas. They're test runs to learn to control the plasma. Yes, tokamaks have also done nuclear fusion. For example, JET, the Joint European Torus in the UK, did produce a record-breaking 69 megajoules of energy in October 2023. That was close to break-even for the plasma, not counting extra energy needed to run the reactor. JET ceased operations at the end of 2023. At this point, it had experienced hundreds of plasma disruptions, sudden losses of control that can slam plasma into the reactor wall. These events aren't just annoying, they can damage the entire machine. This is a common theme that has been observed in all tokamaks. They're a balancing act between Maxwell's equations and Murphy's law. One of the key factors that give rise to this problem is that tokamaks rely on a current that moves through the plasma to keep the plasma confined. If you don't use a plasma current, you need much more complicated magnetic fields. And this is where stellarators come in. Instead of relying on a plasma current, stellarators generate the magnetic fields entirely with coils twisted into complex 3-dimensional shapes. This makes the plasma much more stable, and in contrast to tokamaks, they can run continuously. The reason this approach hasn't been explored much is that for decades, stellarators were incredibly hard to design and build. The magnetic fields had to be calculated with supercomputer simulations, and the coils were often so complex that they had to be bent by hand. Not a joke. Somewhere someone literally hand-twisted a fusion-grade electromagnet. But these obstacles have been pretty much solved now by a combination of machine learning and high-precision engineering. The first recent announcement now came in January from the US company Thea Energy. They published 4 open access and peer-reviewed papers with their design plans for what they call the planar coil stellarator. Their idea is to not use the complicated 3D shape required for the stellarator, but instead simpler coils with computer algorithms to steer the magnetic field. Basically, they move the burden from the hardware to the software. In March, the same company said they tested a prototype of these planar coils, and they produced magnetic fields of over 3 Tesla, enough to confine plasma in a fusion-relevant regime. Just a month later, the German startup Proxima Fusion, which we talked about previously, also published an open access paper with design plans for a commercial stellarator power plant that they call Stellaris. Along with that, they open sourced the code that they use to calculate the plasma behavior. They're working on the magnetic coils and plan to build a demonstration device by 2031. And just a week later, Type 1 Energy, which also works on stellarators, released several papers with their design plans for their planned pilot plant Infinity 2022. This isn't just a concept sketch, it's a detailed, self-consistent model of how to build a stellarator capable of producing 800 megawatts of fusion power. Type 1 plans to have a power plant operational by the mid-2030s. So we have 3 stellarator companies publishing their design plans at pretty much the same time. Coincidence? I think not. I suspect that the Stellarator community is small and tightly connected, and they all know to some extent what the rest is doing. I find this remarkable for 2 reasons. The first is the rapid rise of stellarators as a serious contender and perhaps even the frontrunner in fusion. The second reason I find this interesting is that these are private companies, but they publish their design plans and, at least to some extent, their code. This is certainly partly to make investors confident, but I think it's also partly because the researchers who work on it want to get rich, yes, but they know they're well ahead in engineering anyway, and they want the entire world to be able to reproduce it at some point. That's what progress looks like. It used to take a security clearance to see a fusion design. Now it just takes a Wi-Fi connection. Recent updates of AI models have been somewhat incremental, don't you think? In today's video, I want to try and convince you that this is a temporary slowdown before they reach human-level intelligence. In February, OpenAI released GPT 4.5 that Sam Altman described as the first model that feels like talking to a thoughtful person to me. Maybe it says something about the people Altman talks to that its first users have described the model as a shiny new coat of paint on the same old car, a nothing burger, disappointing and underwhelming. We finally got to use O3, but that hallucinates more than 4.5. Still can't count the R's in strawberry, and falls for the same riddles that LLMs have fallen for since the beginning of time, and it's likewise been described as disappointing. It's a similar story for Anthropic's Claude 3.7 and Gemini's 2.0, and the recent version of Meta's Llama actually seems to be worse than the previous one, which is some sort of achievement, I guess. The current phase of disillusionment was well illustrated in a recent essay by Dean Valentine. He writes, "In recent months, I've spoken to other YC founders doing AI application startups, and most of them have had the same anecdotal experiences. First, O99 Pro Ultra announced. Second, benchmarks looks good. Third, evaluated performance mediocre. Whatever gains these companies are reporting to the public, they're not reflective of economic usefulness or generality. I don't think the models have improved much since August." That agrees with my impression, but I think the reason is that the currently available types of models, large language models, have reached a phase of diminishing returns. We'll only see significant progress when something really new becomes available. And then AI will make another huge step forward, probably reaching human-level intelligence. You know, like puberty, but for software. Several people in the industry also seem to think so. Ilya Sutskever, who used to work at OpenAI, recently said in an interview with Reuters, the 2010s were the age of scaling. Now we're back in the age of wonder and discovery once again. Everyone is looking for the next thing. Google CEO Sundar Pichai also predicts a slow year for AI in 2025. And Jan LeCun from Meta too thinks that it'll take a few years for the next big step to come along.
I'm not so interested in LLMs anymore. So I'm excited about things that a lot of people in this community, in the tech community, might get excited about 5 years from now. Right now it doesn't look so exciting because it's some obscure academic paper.
Obscure academic papers? Hey, that's how we know it's real science. Incomprehensible, published in a journal no one reads, and citing all the author's previous works. For the time being, companies work on unhobbling the current models by giving them more time to think, by giving them better memory, and by letting them use other software, like for maths and figures. Meta announced in December they're working on what they call large concept models. That's basically combining different verbal multiple expressions of the same logical relations to one another. Another improvement for the current models are meta-chains of thought. That let a model evaluate different lines of reasoning. And yes, these improvements should help large language models to grasp logical relations faster and better, but eventually, they're not the new paradigm that we're waiting for. The new paradigm will come from models that learn by interacting with the world and that can continue to keep learning after training. These are the so-called world models. One step towards that is DeepMind's Genie 2, which they announced in December. Genie was trained on a large video dataset and generates interactive 3D environments. They can then place AI agents into these virtual worlds so that they can learn to learn. DeepMind isn't the only one who's announced progress with world models. In January, NVIDIA introduced the Cosmos platform, which also generates three-dimensional models with the laws of physics built in. For one thing, such models can be used to generate videos in which objects don't appear out of nowhere and where perspective is consistent. But more importantly, they can be used to train other models so that they learn how reality works. This makes sense to me because it's how human intelligence evolved. We're interacting with the physical world and creating our own mental models of it. DeepMind calls theirs a foundation world model, and such world models are almost certainly going to play a big role in the next big AI revolution. The next big steps will be systematic upgrades to reasoning capabilities and not just more training. And they're working on it. Basically, the future's here already. It's just stuck in obscure academic journals. A few weeks ago, we buried hydrogen hype. But wait, there's a new miracle fuel on the rise, ammonia. This isn't an entirely new idea, and I was thinking if it hasn't been going anywhere so far, it probably never will. But when I looked into this, I learned a few new things that made me think it's more promising than I thought. Let's have a look. First things first, what's ammonia? Ammonia has the chemical formula NH3, and the good thing about it is that there's no carbon atom in it. This means if you burn ammonia, it produces no carbon dioxide. This is the first good news. The second good news is that it actually does burn, and that does release energy in that process, so you can use it as fuel. Ammonia is a gas at room temperature, but it becomes liquid at much lower pressure than hydrogen gas, which makes it considerably easier to store and handle. It also isn't as explosive. Last but not least, it has a higher energy density per volume, meaning that you can pack the same energy into a smaller space. That was the good news. Now the bad news. Ammonia is toxic, is highly corrosive, generally nasty to handle, and it stinks. When I say it stinks, I don't just mean it's unpleasant. Ammonia was once used to revive unconscious people. That's because it smells so badly, it basically brings the dead back to life. If you wonder how it smells, ammonia is the characteristic stink of urine. It's also really good fertilizer, by the way, so your garden was just doing his job. Another problem is that while one can use it for combustion engines, the energy required to spark the combustion is much higher than for gasoline. It also burns slower, and the combination with oxygen can produce nitrous oxides, which are a health hazard. This means that while one can use combustion engines for ammonia, these need to be suitably adapted. But once you manage to do this, you can run combustion engines carbon dioxide free. This isn't just theoretically possible, it's been done. Already in 2023, Toyota unveiled the world's first ammonia-powered engine for passenger cars. It's a 2-liter 4-cylinder engine, so pretty small, but it works. There are also various companies that develop ammonia engines for heavy-load vehicles and ships. Indeed, the Australian company Fortescue has a prototype prototype for a ship engine that can switch between diesel and ammonia. It's been in operation since last year and just completed a journey from Singapore to the UK. The American company Acer Power is working on conversion kits to replace diesel with ammonia in existing engines. They're initially targeting trucks and tractors, but also electric generators, and who knows, if it goes well, maybe passenger vehicles. But here is a new thing which I only just learned about, which is that there's a company that's working on generating electricity from ammonia to run electric cars with it. They do it by first generating hydrogen from the ammonium. So basically the car's hydrogen powered, but they avoid the problems with transporting and storing hydrogen by using ammonia instead. The startup is called Ammogy, is based in Brooklyn and is backed among others by Amazon and the oil company Saudi Aramco. Why would an oil company back an ammonia-powered vehicle? It's because at the moment most ammonia is produced from hydrogen. And most of the hydrogen is produced from methane, aka natural gas. And that process, you saw it coming, does release carbon dioxide. This is why the fossil fuel industry wouldn't mind switching to either hydrogen or ammonia. It's possible to generate ammonia from electrolysis by first getting the hydrogen from water. Then it'd be truly carbon neutral. Or one could use carbon capture and storage. Another way would be to just use naturally occurring hydrogen. There have been repeated rumors that this might be a much more common occurrence in Earth's crust than we thought. I have to admit that I like the idea of using ammonia to power cars. As I said previously, for the time being, the problem with electric vehicles is that the electric grid extension is lagging behind. This is why we're seeing an uptick in hybrid vehicles instead. Replacing gasoline with hydrogen isn't going anywhere because it's just too difficult to handle. So maybe ammonia is the solution. But wait, there's a big problem here. It's that using ammonia is even more inefficient than using hydrogen directly, because not only do you need the electricity to generate hydrogen, you then also have to produce the ammonia from that and then convert the ammonia back to hydrogen and that into electricity. Each time I think about this, I arrive at the conclusion that fossil fuels are really damned useful. Maybe that's why we haven't stopped using them. Has someone thought of this? I got a few questions about a recent claim that physicists have found a way to correct Einstein's theory so that black holes no longer have singularities. Isn't that kind of a big deal? Why isn't anyone talking about this? Let's have a look. Black holes in Einstein's theory have two defining properties. One is the event horizon, a closed surface from within which nothing, not even light, can escape. The other characteristic property is the singularity in the middle of the horizon. In Einstein's theory, you can't have one without the other. That's the brief summary of the Penrose-Hawking singularity theorem. Whenever matter collapses to form a horizon, it'll also create a singularity. And everything that falls into a black hole will also inevitably fall into the singularity. Once you've crossed the black hole horizon, there's no escaping this fate. Welcome to the black hole California. But what is the singularity? Mathematically, the singularity is a place where time ends. In black holes, it's also accompanied by an infinite curvature of space-time, but most physicists, me included, think that this isn't actually what happens in a black hole. Rather, the singularity is probably just an indication that the mathematics of Einstein's theory breaks down. It's worth stressing that there's nothing mathematically wrong with the singularity. It's just that physicists think it's physically wrong. This is an expectation we take from other areas of physics. Whenever a singularity pops up in the maths, it just means that we're using the wrong maths. Imagine, for example, that a water drop pinches off a tap. If you describe the drop as a fluid, then mathematically there's a singularity at the pinch-off point. But physically, That just means that it's no good to describe water as a fluid at small scales. It really needs to be described by a different theory, one with atoms and molecules and so on. To come back to the black holes, the singularity inside of a black hole is also the origin of the black hole information loss problem, because the singularity is where information goes to die, basically. Physicists usually expect that getting rid of the singularity will require a theory for the quantum behavior of space and time, a theory of quantum gravity. If the authors of the new paper indeed solve that problem, this would be a big deal instead. So what did they actually do? The authors of the new paper say that they can modify the equations of general relativity so that the singularity goes away. The way that they do this is by adding an infinite number of new terms to the equations. These terms are called correction terms, which is why the popular science report says that they corrected general relativity. An infinite number of terms might seem a bit wasteful, but the thing is that functions with infinite terms can behave much more nicely than those with finitely many. Forget about general relativity, just think about a single-valued function, our good old friend f of x. Any polynomial with finite order will diverge at plus and minus infinity, but this is not the case, for example, for the sine function, which is an infinite polynomial. It's basically for the same reason that theories with an infinite number of correction terms can avoid problems that any finite number of such terms would bring. By the way, this video comes with a quiz that lets you check how much you understood. In case the idea with all those correction terms sounds good, well, here are the details. First, their solution only works in 5 dimensions or more, which is clearly stated in the paper, but not so clearly in the press release. This is basically the physics equivalent to saying we have cured Alzheimer in yeast. The other problem is that there are like hundreds of different ways to do the same thing. Indeed, even I wrote a paper about how you can get rid of the black hole singularity by fumbling with the equations of general relativity. So have lots of other people. I'm sure that the authors think their solution is particularly nice, and you know what? I agree, I like it. But does that make it right? Can you test this idea? Well, no, because last time I looked, we didn't live in 5 dimensions. If they can extend their result to 3 + 1 dimensions, which I'm sure they'll eventually manage, then in principle, all these terms would also make corrections at the black hole horizon, and that'd have observable consequences in principle. In practice, though, I strongly doubt that they'd be large enough to measure. But the idea of an infinite number of corrections is generally applicable. You see, if you just make 4 or 5 arguments, the discussion will spiral out of control. It follows that the key to winning an argument is to just never stop talking. Thanks for watching. See you tomorrow.